IoTWeek.
So I think it's time to start this session. I hope you can hear me, and thanks for joining this session. I'm John Soldatos, and this is the training session on machine learning at the edge and the far edge. In 1 hour, together with my excellent colleagues, Artemis Voulkidis and Jans Hagenmeyer, we will try to present the state of the art on federated machine learning, TinyML, and embedded machine learning from different perspectives. So before starting the session, I'd like to take a couple of minutes for a very quick introduction to the topic and to this workshop. First of all, who we are. As I said, I'm John Soldatos, Intrastov International. I'm a member of the EU-IoT project, and together with a group of other Internet of Things projects, we have a series. We organize a series of training workshops. These happen more or less every 2 months. So we had previous workshops on artificial intelligence and Internet of Things and edge machine learning in May 2021, the tactile internet in July. This training session and more trainings are coming up on next generation IoT architectures, 5G and IoT, decentralized IoT applications, and more. So stay tuned before IoTWeek for our training workshops in the EU-IoT webpage. Now, today this is about training and educating and raising awareness about a very hot topic. We know that we have a shift of data from the cloud to the edge to local cloud. This is very evident. This is very topical. It is what is discussed in our community earlier this year. It was a major topic in Hannover Messe, in Internet of Things World, and it is also a main theme in this year's online IoTWeek. One thing is that you get a lot of benefits from doing some of the work on the edge instead of transferring all the data in the cloud. But of course, to have really intelligent, autonomous, energy efficient applications and also secure applications, you need sometimes to be able to run machine learning at the edge. And there are many different ways to do this. Today, we are gonna delve into the details of different techniques, starting from Artemis Voulkidis, company Synellix's IoT engine project, who is going to talk about federated machine learning, shedding also a little bit of light on security issues. Then moving to Battleyard project and Jens Hagenmeyer from University of Bielefeld, who is going to discuss the hardware aspect, which is very critical for the performance of machine learning at the edge. And I will end up discussing TinyML and embedded machine learning and how you can start experimenting with this. So I wish you a nice attendance to the session. Remember, you can post questions on the chat, and we will convey this to the speakers. Of course, we're going to have time for only a couple of questions per slot, since this is really a short and concise session. So without any further ado, I'd like to give the floor to Artemis for his presentation, his tutorial on federated machine learning and cybersecurity issues.
Can you see my screen?
Yes, we can see your presentation, Artemis.
Excellent. Thank you very much. Thank you for the introduction, John. And good morning, everyone. I'm Artemis Voulkidis. As John said, I'm Technical Director of Snellic Solution, and I also act as a Technical Coordinator for the Edge 2020 IoT Engine project. So today I'm going to present a quite concise presentation on federated machine learning and several cybersecurity aspects related to that. First of all, a bit of an introductory part. We are in the IoTWeek plane, so we all know that in a network of connected IoT devices, one thing that first comes to our mind is, of course, security and privacy. So the definition of privacy regarding IoT is that the data collected from IoT devices, they should be made private, so nobody unauthorized should have access to this data. And when it comes to security, we are mostly saying that networks should be secured from cyber threats and attacks. And when I talk about network, it's not about the network part, the core network, such as transmission, etc., but also the devices. So we argue in this presentation that federated learning may be exploited to empower, let's say, distributed machine learning in a way that we can ensure cybersecurity and data privacy. So let's see how this goes. First of all, an introduction to federated machine learning, how it is and how it works and what exactly it is. So as you can see in the figure, we envisage the IoT edge and cloud continuum. So we have the IoT nodes. We could have some IoT, some federated learning clients in this node, or we could have aggregated, let's sort of aggregated federated learning clients at the edge. Long story short, there is some machine learning happening at the FarEdge cloud or the near edge, and then this machine learning takes place over the local data. Now, as soon as these federated learning clients perform their model training on the local data, they send the models to the federated learning server, usually located at the cloud, could be also the edge depending on the application. The FL server then performs an aggregation function on top of these models and then redistributes all the models back to the clients. So the main objective here from our side is that, of course, each IoT node is able to perform the training based on its own data, but then the model it receives is trained over the data of the entire federation. So that's a huge plus when it comes to the accuracy of the model that's been served as an outcome, for example. Regarding the security and privacy part, though, the core advantages, mostly it is related to the fact that the data itself is not transmitted. So it's only the models that get transmitted and not the data. The network traffic is less because the model, so the training results, they are much smaller in size than the data itself. And when it comes to traditional distributed machine learning, federated learning needs quite less of computational resources. So this goes back to what John said about energy efficient, for example, edge operations. Having said that, so okay, we don't transfer the data, so this means that all the federated learning part is privacy guaranteed, let's say. The short answer is no, because data attacks at the network level, they are guaranteed not to happen. But then we do have several attacks against the federated learning processes, mostly regarding data poisoning, so leading to mislabeling and false labeling. Another thing could be model poisoning to adjective model changes. And then we also have re-identification attacks where an attacker, let's say, could exploit similarities to other datasets to expose the data characteristics. So now I'm going to overview a couple of these attacks to understand the core context. So the first one is trying to insert false data during the training to lead to false labeling. As an example, we have an image of a panda, let's say, and if we add the gibbon class gradient to it, then and pass this image to the federated learning clients, then we could, in the end, arrive to a situation where you give a panda image and it gets identified as a gibbon. So this is a classical data poisoning attack. You poison the initial data, the training data, and then you can affect the inference outcomes. Moving on to a re-identification attack, we have here two images. So the right one is the initial image that was used for training, and if an attacker is given a person's name, so the name of this guy over here, and has access to a facial recognition system plus the confidence level scores, then it is proven algorithmically and practically that one could, through reverse engineering, let's say, identify an image or sort of an image, noisy part of an image that was used for training. So this is a re-identification attack and focuses, of course, on privacy. So we said that federated learning is more private. Then we saw that it's not private. But can it be guaranteed? The short answer is mostly yes. There are some techniques that can be used, like homomorphic encryption, secure multi-party computation, differential privacy, and of course private hybrid methods of those that can be used to guarantee privacy from these different perspectives. So the first one is homomorphic encryption. I guess some of you might be already aware of what this exactly means. In short, homomorphic encryption allows certain mathematical operations, such as the aggregation functions that I mentioned before about the aggregating part of the federated learning operations, to be performed directly on ciphertext. So without decrypting, let's say, the models per se, we can still have these aggregate functions and then transmit things encrypted once again. So what does it exactly mean? When we have the federated learning clients, before sending those, all the models get encrypted. The aggregator performs the aggregation without decrypting, and then the still encrypted parts, so model updates, get transmitted to the federated clients. Most problematic part of this homomorphic encryption approach is that it needs an external party to hold the secret key, something that's not standard in the federated learning setting. So we need a trusted party. That's not good. And depending on the mathematical operation to be applied on top of the modules, this could be computationally costly. Another attempt towards ensuring privacy is differential privacy. The scope is, again, to limit information disclosure, but the take is a bit different. So what differential privacy does is that it adds noise to the released model sufficient to mask the value of each party. And it relies mostly on the fact that deep learning models are resilient to minor changes. So if we selectively apply this noise part when applying it, then we could end up with having the same kind, let's say, of accuracy without sending the exact models that should be in aggregate being sent. So this is fast to calculate while preserving high privacy standards. It's well suited for large data sets. And in this slide over here, we present an example of this approach, a differential privacy-based framework called PATE. The core concept behind PATE is to split the data set into two parts, one private and one public data set. We have an ensemble of teachers, so a set of clients operating on top of private data. Then we have an aggregate teacher, like the federated learning server that I showed in the previous figure. The aggregate teacher, so the server, calculates the private part of the model, so this predicted completion that I mentioned here. Then the noise gets added with some incomplete public data, and then the final inference part takes place at the students. And it's the students where the attacker may actually have access to. So still the models that get transmitted, they're kind of noisy. So now let's see, let's dive into a bit of cybersecurity and see how we can employ federated learning towards that direction. So cyber securing both the learning process and some systems relying on federated learning. So regarding the definition of a cyber intrusion, we'll pretty much understand what it means. There's an attacker and tries to attack and compromise a computer, break the security systems inside this computer and the network in which this computer resides. The overall concept is to make the computational environment unsafe for operations, perhaps also extract some data. So machine learning, it can be applied to the attack detection, mostly towards two directions. The first one is signature-based techniques, like antivirus, for example, work. This is used to detect known attacks by using specific traffic characteristics that characterize these attacks in the network traffic, let's say. And then we also have anomaly-based techniques, where we actually model the normal behavior, for example, of a network, and anything abnormal, so an outlier to this normal behavior, is classified as an attack. Core, let's say, benefit of this approach is our ability to detect unknown attacks. Still, the caveat is that when there are times that we don't know exactly what's the problem, we know that there is a problem, but we're not sure exactly what the problem is. So normally, classical machine learning may be employed, let's say, to perform these types of intrusion detection, like classification or time series analysis and stuff like that. In this presentation, we present generative adversarial networks, a technique usually used to generate synthetic data, but which can be also used as an intrusion detection system. Not only that, but also for malware detection and for identifying defense strategies against different attacks. So let's see what generative adversarial networks are. So the goal is to learn from a set of training data and generate new data with the same characteristics as the training data. So consider this image on the left side of the screen. We have a known data set that feeds first a discriminator, which tries to model this training data set. And then we also have a generator. Now the generator, what it does is to produce permutations of this training data set and pass them to the discriminator to check whether the discriminator thinks that this modified or false, let's say, data set present a normal or an abnormal behavior. So whenever the discriminator says that, okay, this new data set that you provide me is obviously false, then the generator changes itself to generate permutations that could in the end be classified by the discriminator as normal. So the generator actually acts as an attacker, a flexible one that is able to also change its behavior over time. And the discriminator is actually the detection part of our system. In machine learning words, the discriminator acts as a multi-class classifier, and the generator acts as a different source of information by permuting raw and labeled training data. So in the context of IoT engine, MAD, so the malicious attack detector, is actually the discriminator of the generative adversarial networks that we showcased in the previous slide. Within the context of the project, we are actually training this discriminator with data sets, open ones, that are relevant to exploiting network logs or model poisoning data sets and stuff like that. I have some examples of this over here. Now, the next part is to mix everything together and see how all these heterogeneous things that I mentioned before, they can actually be mixed to produce something that is meaningful. So with regards to federated learning and PATE, so differential privacy, as I said before, it's the federated learning clients that act as the teachers in the teachers ensemble, as I mentioned before. Then we have the model transmission all the way towards the federated learning server, which actually is the teacher aggregator. And then we do have, at that point, over here at the federated server application side, the student part. So mixing with noise and offering the inference part to the outside world, hence also receiving all the relevant attacks. And when we introduce the GAN approach as well, and considering a federated learning setup with 2 clients, then the figure may be transformed into this one. So in each edge node or IoT node, we could have the client's sensitive data training the teacher. This means that we have the federated client there. Then we forward the model to the federated learning server protected by a MAD. And then on the client side, we also have a malicious attack detection part regarding the models that can transmit it from the federated learning server back to the federated learning clients. So in this particular setup, we do have the differential privacy offered by Pate, and we also have the security against the model changes offered by the generative adversarial networks part. So some key takeaways and conclusions from this presentation. If we could keep something, of course, it's that the federated learning is a great candidate for next generation IoT networks. Having privacy considerations and cybersecurity ones might make it a bit more complicated, or let's say computationally heavy, but still there is an urgent need to protect the data, the models, and the inference processes. And we argue that perhaps a framework towards the right direction could be the combination of federated learning plus differential privacy plus generative adversarial networks. So that's it for now. Thank you for your attention, and I am open to questions or any suggestions. I think that we have 2 or 2.5 minutes more. Thank you very much.
Unless I'm mistaken, I don't see any question, Artemis, in the chat, in which case we could pass the floor to Jens.
Excellent. Thank you.
Okay, I will try to share my screen. Give me a second. Sorry. I guess you can see my screen and hear me fine?
Yes, we can see the slides.
Okay, great. So welcome everyone. And yeah, as the previous presentation was more on the security side, I will now, as already introduced by John, focus more on the hardware side of things. I'm presenting, so the results or the architecture I'm presenting is part of the Battleyard project. The Battleyard project is basically focusing on very efficient deep learning for IoT. It consists of, on the one hand, the hardware platform, which I will introduce in more detail in a second. Then there is also the accelerators. In Battleyard, we are looking at basically what we call co-design of FPGA and the application by using FPGA and ASIC technology to then really boost the efficiency of deep learning applications for IoT, as well as the toolchain part. We have use cases in the project from industrial, automotive, as well as smart home. And there's also an open call which will be presented in more detail later on today in the open call presentation. So make sure you don't miss that. Short introduction to Battleyard. As said, we have, it's an EU-funded project. There's a couple of partners from both universities, bigger industries like, for example, Siemens, and also smaller SMEs like, for example, Embeddle and Micro. And we are spread all over Europe from Portugal to Sweden. The structure of it is like this. As said, we have the hardware at the bottom, then the accelerators and the tool chains, which are then building on top of the use cases. We also have a focus on security and privacy. Let's say not focusing on similar parts like the ones that were just mentioned by IoT Engine, but focusing also on things like robustness and safety, especially when you are in this automotive area. You need to handle a lots of aspects with respect to safety. So is it okay to deploy machine learning models in areas where you require functional safety? What will happen when you do this? You do the same in an industrial or in a smart home environment, and so on. With respect to the ambition, we are looking at having these reconfigurable, heterogeneous, scalable IoT platform, and we expecting a 10x improvement in performance by applying these hardware accelerators, as well as a 10x improvement in efficiency by applying these toolchain, which then maps the models, so the deep learning models on these heterogeneous hardware and on the accelerators in an automated way. So as said, I'm starting off with the hardware platform of Battleyard. Basically, what this platform aims at is integrating various technologies, various processing architectures like x86, RISC-V, embedded GPUs, regular GPUs, so to say, specialized ASICs, FPGA technology that was already mentioned in a comprehensive single platform, which can then be used for edge or far edge computing, as it is the topic of today's session here, or even then going really up to cloud computing domains, which basically then simply the simple change then is here really the number of what we call microservers. So we encapsulate all these architectures in computer on modules, which are basically microservers, which are then deployed into these hardware platform, which we call Rexbox, T-Rex, or micro-Rex. As said, all this is heterogeneous, modular, scalable. We are having a particular emphasis on the communication infrastructure, and we then cover, let's say, everything from embedded, so really small, tiny nodes, over far edge, near edge towards the clouds. And we are aiming at improving performance, maintainability, energy efficiency, especially based on the integrated accelerators. Typically, performance comes with it, but also things like reliability and safety by the integrated monitoring aspects. How is this composed, or how can you think of the architecture? As said, all this is modular. So when we are looking at these bigger systems, that are called Rexbox, we are having a couple of different microservers, then also covering the different architectures. So you can think of, okay, if I have a normal x86, it goes into one microserver. If I have an FPGA, it goes into another microserver. We are distinguishing different kinds of compute power classes, or different types of performance classes. On the one hand, what we call high performance microservers here. On the other hand, the low power microservers. Those are then populated on carriers, which provide monitoring, which provide communication, which provides all the power for sure. So all the infrastructure that you need to operate those. And then we can also add, for example, normal PCI Express based accelerators, which are then, as said, are added to all these communication, monitoring, and high-speed, low-latency communication issues that I was just mentioning. As said, we have a focus on, let's say, also supplying the communication. That's why we, apart from the normal Ethernet communication within the system, we have a high-speed, low-latency network. Because typically when you are in these distributed environments, communication is something that then really matters, and that in the end affects your performance if you're not careful of addressing those things. Then this thing can be scaled down. If you remember, apart from the Rex box, we had also the T-Rex that is optimized for the edge server applications. It's basically the same thing. It's more compact, so to say. It cannot integrate that many microservers. In the previous system, the Rex box, we had up to 144 microservers. Here, this is reduced, but we have added more connectivity for really attaching I/O devices to the edge server, as it's typically needed in a near edge application. And then when it then goes forward to the FarEdge, we have a device which is currently under development called MicroRex. It will also integrate computer on modules. So these things that we call microservices again. In particular, we are looking at SMARC and Jetson NX here, coupled to an accelerator in an M.2 form factor, which then again follows the same modular scalable concept as you had for the two more powerful platforms, but really then scaled down to requirements that you typically have at the FarEdge or in the embedded domain. So all this, again, here not only support CPUs, you have SMARC modules for FPGAs, for example, as well. We have all the GPU part in it, and within the project, we are also developing our own microservers. So when you have a look at this here, this is the microserver overview, which can then be populated on those different platforms. We are, for example, looking at dedicated accelerator ASICs, which we are then integrating into, for example, a SMARC form factor and deploying onto the platform. So what you have in the end with all these Rex platform is then a really scalable, heterogeneous processing platform, which you can easily deploy, which you can easily monitor your application on, and which is then basically coupled also to this accelerator and to the toolchain part within Battleyard that allows you to deploy your IoT application in a nice way, so to say. As said, the hardware is one thing. I will also cover, let's say, the other aspects in a quick manner. So one thing which we are doing is also optimizing the algorithms. So to map them on the hardware by developing dedicated accelerators. So the normal way, so to say, that is something that you can just do relying on the hardware, is to really select the most or best suited, the best fitting hardware platform for your application. So as said, the platform supplies you with CPUs, GPUs, ASICs, FPGAs, so you can just choose the optimal optimal hardware that maps to your application, and you can also benchmark. So you can just test. We have different test beds available, integrating all those technologies. So you can just test. Okay, I can then do a profiling with respect to, on the one hand, performance, on the other hand, communication, and also energy. So let's call this energy and communication aware profiling, what then best suits your application, and then you can just modify and select the hardware in a, let's say, plug and play manner to best match your application. But something which is also done in the project is what we call architecture, which is then really co-designing on the one hand the accelerator, for example, based on an FPGA, because FPGA technologies allow this, and also the deep learning model. So really, looking at both sides, optimizing to then even have a better fit than you can have by just selecting a pre-existing hardware model. And then all this is then let's say added or guided by a deep learning toolchain. We have a partner in Battleyard, Embeddle, which is a spin-off out of Chalmers in Sweden, which is focusing on exactly this. So really having a toolchain which are not looking at optimizing one particular framework which is already there, but just by combining the different frameworks and formats which are there by the runtime, and also by really adding the support for the different heterogeneous hardware platforms. So it will optimize, it will map, and it will also help you profiling this whole thing in the end. Quickly, a short introduction to the use cases that we already have, and we expect to have additional use cases by the open calls within Battleyard. On the one hand, we are looking at a smart home. There we have a smart mirror in the project, and we are seeing this smart mirror as the central user interface for the smart home, because the smart mirror concept allows a quite intuitive control. It's doing, for example, gesture recognition, voice recognition, face recognition, and then displays personalized information as well as interacting with all the different aspects of your smart home. For sure, data privacy here is a high priority. That's why we are trying to do everything locally. So really, as an edge setup, and not doing any computation, let's say, via some public cloud infrastructure. As said, what is used in there? So this is really something which requires quite some computational, demanding applications. So we are doing face recognition, object recognition, gesture recognition, speech recognition. So all this then in the, let's say, easy case, maps to just using some workstation hardware. This is for sure not an option here, because we want to have this whole thing consuming not 300 watts. We are more looking at 30 watts or 10 watts. So this is something where all these techniques that I was just trying to describe, the hardware as well as the toolchain and the accelerators, really kick in and boosting these use case to keep the performance while being far more energy efficient than before. On the other hand, we have the industrial IoT use case. Drive condition classification, where we are using IoT technology to then basically doing a predictive maintenance use case. So without really measuring the motor current or the motor voltage, just by attaching this device here to the motor, we want to predict when the device is going to fail. We want to predict when maintenance is required, and so on. Another thing is that we are also looking at in a similar context here is architecture. So within a switching cabinet, you are typically having you are very afraid of arcs, so electrical arcs going to happen. So the let's say specific requirement of this application is the safety criticality. So you need to have a very high accuracy here. So let's say false positives or false negative in this application are really being a problem, because you want to make sure that when you're detecting an arc, it's really not an arc. Otherwise, you're just switching the complete thing off for no reason. And when you're let's say missing an arc, it can be really going to be a problem for the operator in the end. Then we have also the automotive use case, focusing on a collision detection or avoidance scenario. The idea here is to improve the performance and cost ratio by really doing AI processing not in one central unit, but really all over the place. So from the small ECU really to the then edge or cloud, by really pushing the different parts of the algorithm on the different hardware substrates here, respecting the changing environment. For example, whether you have 5G connection, whether you don't have 5G connection, whether you are in a city environment, whether you are in a countryside environment, and so on and so forth. So that's the quick presentation of Battleyard. As said, if you're interested in the open code, so if you want to use Battleyard technology, make sure you don't miss the presentation in the afternoon here for IoTWeek. Thank you all.
Thank you, Jens. We have a question, right, on the chat. I don't know if you can see it or if you want me to read it. It is about.
Great if you can read it. I don't see the chat because I'm presenting.
The question by Mr. Koutsopoulos is whether there is any how-to or guide that, as far as I understand, hardware vendor or hardware prototype developer can make their platform compliant to Vettel IoT and become part of your ecosystem.
Yeah, so we are using, as said, we are using common computer on module standards, like for example COM-HPC, like COM-Express, like SMARC, and so on. So if you are, and we are also, let's say, are part of the working groups which define those standards. So for example, COM-Express and COM-HPC are defined by PICMIC, and we are part of the PICMIC working groups there. If you respect those standards, it makes integration easy. It also means that the hardware platform itself is open, so we can normally quite easily integrate third-party hardware there. And for specific requirements with respect, for example, monitoring and so on, we should have a private discussion.
But are you going to publish also some public information about the compliance and the protocols, or maybe this could be also a theme of the open call, right? If you want to extend your ecosystem.
Yeah, so for the open calls, there will be because our open call is starting next year. There will be a package supplied to open call participants, how to use this and what are the interfaces and so on. We also have something just published because we just had one of the main milestones, but I guess those deliverables are not yet approved, so they are not already available online.
Okay, thank you very much, Jens. If there are more questions, of course, we can take them till the end of the session. But for the remaining time, I will proceed with my presentation, and I would take the opportunity to highlight how exciting is edge computing, but also how broad it is, because we see through this hour how you can do edge computing in many different ways. So in this presentation, I'd like to talk about TinyML and embedded machine learning, starting with motivation, which is, do we really need always to run machine learning on GPUs in the cloud, or even on the nice hardware accelerators that we've seen before on the edge? Certainly, it is very useful for some demanding use cases. It's a prerequisite for some demanding use cases. But there are also use cases where you might want to run machine learning directly on the microchip or on your microcontroller. And if you do this, we could conveniently call this machine learning not at the edge, but actually at the far edge. If you do this, you push the benefits of edge computing to their limits. So you can really have the lowest latency possible because you don't deal with any networking operations. You have really the most power efficient operations as you keep I/O and all other energy consuming operations to the minimum possible. And let me open my camera. Sorry about this, that you can also see me. So you get all the benefits of edge computing. I'm not repeating each one of them to the best possible limit, right? You push the benefits of edge computing to their limits. So you can have the greener edge computing, the most privacy friendly, and so on. So if your use case allows you to do this work on this machine learning on the microcontroller. And I have here some different considerations so that you can think of the trade-offs. Okay, so really, if you care about having availability of many data points, it makes sense to go to the cloud, right? And then, of course, if what you care about is energy efficiency and green computing, then running AI on GPUs on the cloud is not the greenest thing you can do. Whereas when you run this at the edge and mostly at the far edge, this gives you huge green benefits and sustainability benefits. Likewise, with other considerations like privacy or real-time performance. And to make this practical, I've taken a couple of very popular use cases from the industry. So manufacturing, but also other industries where we have asset management and maintenance of assets and also production quality. So if you imagine the very popular use case of calculating the remaining useful life of an asset or of detecting a possible defect, then if you are able to do this inside the machinery, inside a microcontroller in the machinery, then this can be much faster than doing this on the cloud. Of course, if you want a detailed RUL remaining useful life calculation, maybe you need more data points and you need a cloud edge interaction, and you cannot afford to do this on the microcontroller. So this is a trade-offs game, and there are also other technologies that can help you also run models without too many training data and too many data points. I've given transfer learning as an example. Now, is it possible to do today TinyML? And there are many boards that you can play with them, you can learn them, you can train yourself with building TinyML applications, maybe this is also a very good idea for the supporting your participation in the hackathon later on, or also proposing cool things in the open, useful things, of course, in the open calls of the different projects, and even being able to get some funding for building your prototype. So here I just pick up 3 boards. There are many more different ecosystems that will support TinyML. The ones here are the Spark Fun board, Apollo 3, also the Arduino Nano 33 also supports TinyML development. And also there are boards from Infineon, ST Microelectronics, and so on. Now, this is not extremely difficult, right? Building a TinyML application, but it really becomes challenging because you need to combine skills from 2 different worlds. And the one world is the embedded application development, if you want IoT development or IoT hacking, and the other world is the data science or the machine learning world. And we know that it is challenging to know each one of these 2 disciplines at the first place, and you can imagine that it is a rare virtue to have developers or people that they are skilled on doing both. Other than that, the process of building applications is leveraging popular tools that we have in those 2 communities. So like the Arduino integrated development environment for embedded development, or Python libraries and Jupyter notebooks for building machine learning applications. And especially for TinyML, there are machine learning tools that help you shrink the size of your models and then deploy it on CPU-constrained devices, like a microcontroller or an embedded device, where your model consumes very few kilobytes of memory. So these tools are the TensorFlow Lite, so the Lite version, the version of TensorFlow for mobile and embedded devices, and the TensorFlow Lite Micro. Let's see how it works, right? It looks like a classical data science or machine learning pipeline. However, you've got to pass it to the embedded device. Now, data acquisition is interesting and is challenging because you know that having the right data for training models is always a challenge. Now, having data that have been acquired from embedded devices or embedded machinery can be a greater challenge. Of course, there are such open source data, and you can find data sets for TinyML in ecosystems like Edge Impulse. I'll talk later on about this. Then once you have some training data set, you need to train a deep learning model. You see, I'm not talking just for simple machine learning models, but you can train some artificial neural network or recurrent neural network using Python libraries like TensorFlow, NumPy, and so on. So all the process is as usual. You've got to have your training data set. You keep part of it for training, like 80%, and you retain another, for example, 20% for testing. And then you build your model, and of course you've got to run this process iteratively to make sure that there is no overfitting or underfitting of the model. So you may have to retrain, reevaluate, test different models or your training data. Then once you have your deep neural network, and this has a decent and acceptable performance for your application at hand, you've got to work with TensorFlow Lite. And you've got here 2 useful tools. One is the converter, which is going to convert the model into a special space-efficient format which can be used on embedded devices. It turns out that the mathematical computations that we do in a deep neural network, we can run them even on a microcontroller, but shrinking the model size is essential here, and it's also important for running it on small devices. And then you've got the TensorFlow Lite interpreter, which is going to convert the model, the TensorFlow Lite model, and make it more efficient for a particular device. Now, at this part, you will effectively get an Arduino, for example, sketch, like a C sketch, which is appropriate for a deployment on the embedded device. Now, TensorFlow, maybe some of you are familiar with popular KPIs like Keras. Well, when you work with TensorFlow Lite, effectively you are working with a little bit of lower level APIs, right? So you've got to allocate memory, read values, and write them in a memory array, and so on. Well, if you are an embedded developer, that's you should be very familiar with this. If you come from the data science world, it's a bit lower level. Then you've got to build a binary for on-device inference. So you've got to run some make command. Of course, you can use the Arduino IDE to do this. In the end, you can run your entire process in your computer, but in the end, you've got to deploy the binary to the microcontroller. Now, the good news is that, of course, you can work with all the popular tools like Jupyter Notebooks. So I mentioned Python, Arduino IDE, but you can have even more automation in the community nowadays. Thanks, for example, to the Edge Impulse AutoML tools, which also they support out of the box a very rich set of boards, and this list keeps on going. And even if you don't have a board or you don't feel buying one, you can build something and learn how to build an application using your smartphone. And there, you've got even more user-friendly tools, AutoML, where you can train the neural network, run the classifier, rerun and reevaluate it, and so on. This is part of the Arduino tutorials. Now, so that's how you can start doing things with TinyML. Of course, if you go to a production environment, we know that requirements are much more challenging because what we build has to work for real. But if you do this good way, you can get huge benefits for some applications. I don't have any slide with use cases here, but just to give you some ideas, imagine, for example, applications like cattle monitoring in large rural areas. There you cannot take connectivity for granted, so being able to monitor the cattle through a chip inside the animal can be very useful. Imagine being to detect a problem with a plant or crop by deploying something directly on the plant. Imagine the industrial maintenance example or quality control example where you can have the fastest defect detection possible, which is really key for avoiding production downtimes and taking remedial actions in a timely fashion, and so on and so forth. There are many use cases where TinyML and embedded machine learning make sense. Of course, I know that we are just scratching the surface when we just deploying a model on an embedded device, because in an industrial environment like a factory, you're likely to have more machinery, more different devices. You might need to deploy on different embedded devices. Then again, there are many things to be done for building tools and making the whole embedded development and data science process a one-click process. having out-of-the-box ML pipelines, and also integrating with some of the ideas we've seen before, like with the federated learning ideas. Remember, with federating learning ideas, you have a privacy-preserving way to share data and models at the edge. And these can, in principle, work with TinyML devices, and you can get benefits from both worlds. So my time is up. I just want to point you to some resources for further reading and further training, like Get It Started Guide from Edge Impulse. There is a Coursera course. It's a rather new course. It appeared during the last couple of months on Introduction to Embedded Machine Learning with a lot of TinyML aspects. There are TinyML books, like in the tinymlbook.com. You can find a book there or purchase it from O'Reilly, I think, is the publisher. Thank you for your attention, and thank you for joining the session. And I really hope that you find what we presented here useful. It's really the core, it's really at the heart of the IoTWeek, since we will be discussing throughout the week for edge computing, edge cloud interactions, and also AI at the edge, machine learning at the edge, and different ways to do this. So unless there is any question, I would like to thank you very much and to conclude the session. And also thanks very much to Jens and to Artemis for their excellent presentations. Okay, so remember the follow-up things, remember the hackathon, remember the project's open calls. We already have given very good ideas that we expect that you might want to bring, also as applications to the open calls of the project. Some of them will be launching open call soon. I think as Jens and Artemis explained, that for these two projects, this will come a little bit later, but still you're going to have the opportunity to apply and work on this very interesting stuff presented today. Okay, Jens, Artemis, I don't know if you want to say anything or we can conclude the session from your side.
Well, thanks to you, John, for hosting this. Thanks to everyone who attended. Thanks for having me. Bye.
Same from me. Thank you all. Thank you, John, for the organization and the rest of the team. Hopefully, IoTWeek will be a success overall. Thank you.
Thank you very much, Artemis. Bye. Enjoy the rest of the sessions and the rest of the IoTWeek. Bye-bye.